A dynamic equilibrium is where the forwards and backwards directions of a reversible reaction occur at the same rate. At the macroscopic or large scale, it doesn't appear that any change is occurring, whilst at the microscopic scale, reversible reactions are constantly occurring at the same rate. The background image for this resource shows an example of a static equilibrium. The stones remain balanced and don't move. Imagine, however, we had a man on a travelator walking in the wrong direction. It's possible that he could be walking at the same speed as the travelator, but in the opposite direction. If we were to take a long exposure photograph, the position of the man would not appear to change, even though both he and the travelator are in motion. This would be an example of a dynamic equilibrium. The rate of the forwards reaction is being modelled by his walking pace, and the rate of the backwards reaction by the speed of the travelator. Changing the conditions would change the position of the equilibrium. For instance, a drop in speed of the machine would cause the man to slowly move forwards. Of course, here is where we need to adapt our travelator in order to make the model fit better. A chemical equilibrium can only be established in a closed system. That's one in which no chemicals can enter or leave. In our model, the man will eventually walk off the travelator, so he's not in a closed system, and a new equilibrium won't be established. In this animation, when you click React, the simulation will roll a virtual dice to see whether the blue particles of A will react and become pink particles of B. A has a 50% chance of becoming B, B has a 20% chance of becoming A. Have a look and see what happens. What is it about the graph that tells you you've reached a dynamic equilibrium? What differences would you expect to see in the behaviour of the simulation if you made the odds 5% and 2% respectively instead? Le Chatelier's principle states that if we have a system under dynamic equilibrium and we adjust the conditions, the equilibrium will move to oppose that change. To help us consider the position of equilibrium mathematically, we express the proportions of our chemicals in the mixture as a fraction. The molecules on the right of the expression appear on top. The numbers of each molecule in the equation become the indices in the Kc expression. Remember that although we can determine the indices for Kc from the equation for the reaction, we're not able to do so when constructing the rate equation. In that case, we need to determine the indices by experiment. If you're interested in writing expressions for heterogeneous mixtures, more info can be found by clicking the highlighted link. Kc is affected by temperature, but not by pressure, concentration, or catalysts. Catalysts only affect the activation energy for the reaction, allowing the forwards and backwards reactions to occur more quickly. The reaction will reach equilibrium faster, but the position of the equilibrium will be the same. For an explanation of the effect of pressure and concentration on Kc, you'll need to see a later slide. This diagram represents three values of Kc. What's the connection between Kc and the position of equilibrium? There'll be a question about this on the next slide. If you're not careful, it can be easy to confuse yourself when working out units. There's a quick way of looking at it and a slightly longer way of doing it, where you're less likely to make mistakes. First of all, write out all of the units as you have them. In our case, we have one lot of moles per decimeter cubed on the top and 3 on the bottom. Multiplying these out, we get moles per decimeter cubed on the top and moles cubed decimeter to the minus 9 on the bottom. Lastly, laws of indices mean that if we have a power of 1 on the top and 3 on the bottom, we need to do 1 minus 3 equals minus 2 as the power for moles, and for the volume we have minus 3 minus minus 9, giving us plus 6. If you feel you might get confused looking at index laws, you can always write out all of the units multiplied out. You can then cross out the ones that cancel. That leaves us with 2 lots of moles per decimeter cubed on the bottom. Multiply them together, and because they appear on the bottom of the fraction, they need to have their indices multiplied by minus 1. This gives us the same answer, thankfully. In experiments, we may be able to calculate the amount of a product at equilibrium and use this to work out Kc. A classic example of this is the esterification of a carboxylic acid. Here, the amount of acid can be titrated afterwards to find out how much is gone, and therefore how much product has been made. In our example, we're going to be adding 4 moles of acid to 4 moles of alcohol. After it's reached equilibrium, we're left with 3 moles of acid. That means 1 mole of acid has been used up. The first thing to do is to look at the stoichiometry of the reaction. For every 1 mole of acid we use, we'll need 1 mole of alcohol. That means in this example we'll use up 1 mole of alcohol, leaving us with 3. Looking at the stoichiometry of the product, we can also see that we'll produce 1 mole of them as well. Our concentration at equilibrium is going to be our number of moles divided by our volume. Let's bring up the equilibrium expression and put in the figures. This gives us concentrations as 1 over V each on the top and 3 over V each on the bottom. Because there are the same number of volumes on the top and on the bottom, they're going to cancel each other out. That leaves us with a Kc of 1 over 9. There are no units here. Sometimes we have to be careful that the stoichiometries on each side match up. 4 moles each of sulfur dioxide and oxygen are allowed to come to equilibrium in a 1 decimeter cubed vessel, and it's found that there is 1 mole of sulfur dioxide left. How are we going to find out what Kc is? This time the important thing to notice is that the stoichiometries are not the same. We've used 2 moles of sulfur dioxide, but for every 2 moles of sulfur dioxide we use, we only need 1 mole of oxygen. So the number of moles of oxygen at equilibrium is 3. For every 2 moles of sulfur dioxide we use, we're going to produce 2 moles of sulfur trioxide, so we'll have 2 moles at equilibrium. Now we can carry on exactly as we did before. This time we've put in our concentrations. Notice also that because the units don't cancel, we've had to put in the volume. If we plug in those values into our equation, we can see that Kc is 0.3 recurring moles to the minus 1 decimeter cubed. We can talk about concentrations of gases, but it's more common to measure their pressure. Kc tells us about the concentrations of components in a liquid mixture at equilibrium. The equivalent in gases is to talk about the partial pressures of the component gases. The first thing about pressure is that it has lots of different units. The best thing to do is to stick with the ones you've been given, unless you've been told otherwise. Imagine we have some particles in a container causing a pressure of 100 kilopascals. What would happen to the pressure if we added another two particles at the same temperature? Of course it would double. The red particles and blue particles are both contributing 100 kilopascals to the total. We call these their partial pressures. The pressure the gas would exert if it was the only thing in the vessel. So the total pressure is equal to the sum of the partial pressures of the gases in the vessel. Another important quantity for describing any mixture, and that's not just gases, is the mole fraction, chi. Don't let the fancy symbol confuse you. This does exactly what it says on the tin. It's just the fraction of the number of moles of a substance over the total number of moles in the mixture. So in our example here, we have 78 particles in total. Of those, 71 are blue. So the mole fraction of blue particles would be 71 over 78, giving us 0.9. The partial pressure of a gas can be connected to its mole fraction by Raoult's law. The partial pressure of a substance is equal to its mole fraction multiplied by the total pressure of the system. Raoult's law holds true for ideal mixtures. Here we assume that all the particles are similar in size, shape and intermolecular forces. This makes sense if you think about our previous examples. There, half the particles were red, giving us a mole fraction of 0.5. In other words, we were saying that the partial pressure is half of the total pressure. An example of a non-ideal mixture would be ethanol and water. In the UK, alcohol is sold as percentage by volume, ABV. However, if you were to get 50 ml of water and add 50 ml of ethanol, you'd get less than 100 ml in total. So in reality, when you buy some beer of, say, 4.5% alcohol, you're getting less ethanol than you might expect. Now that we have the tools to describe the equivalent to concentration in gases, we can write our equilibrium constant for gases, Kp, in exactly the same way as before. So for a reaction where A is in equilibrium with B and C, Kp has the products on the top, that's B and C, raised to their respective stoichiometric powers and divided by the reactant A raised to its stoichiometric power. Note that the square brackets denoting concentration are not needed here. For example, the Haber process could be expressed as the partial pressure of ammonia squared over the partial pressure of nitrogen times the partial pressure of hydrogen cubed. The equilibrium between nitrogen dioxide, which is brown, and dinitrogen tetroxide, which is colourless, is sometimes the subject of an undergraduate practical. These bottles initially contained equal amounts of both gases. One bottle was cooled and the other one was heated. It's important to be able to understand the reactions of nitrogen dioxide, as it's a key pollutant released into the atmosphere during the burning of fossil fuels. A question that often gets asked is, why is it that both Kp and Kc are unaffected by changes in pressure and concentration, even though the position of equilibrium can be affected by these things? If we substitute in Raoult's law, we can write our expression like this. However, big P, the total pressure, appears twice on the top and on the bottom, which allows us to cancel it. So Kp is independent of pressure and depends only on the mole fraction of its components. Life isn't always as simple though. In this example we have a different number of components on the top and on the bottom of our equation. Let's for the moment assume that we're correct, and that Kp doesn't change when we change, for instance, the partial pressure of A. What's going to have to happen in order to keep Kp constant is that some of B and C would have to be used up and go back to make more of A. This would mean that overall the value of Kp would remain the same, even though the position of the equilibrium would have shifted. That concludes this activity on equilibrium.